Welcome to a webinar by Geophysics on the geophysical survey method AMT and the possibilities that it has for your site characterization. AMT is another tool that you can add to your site characterization toolbox. Now you might be wondering, what is AMT? Why should you choose to use HGI for your AMT geophysical surveys? And how does it work? Well, we're here to answer that today. HGI is a solution-oriented geophysical consulting firm and service provider to the environmental engineering, groundwater, mining, geotechnical, and natural resource exploration industries. HGI specializes in applying geophysical characterization methods to subsurface monitoring of fluids and geologic materials, to liner leak location, and of course, in the case of basin characterization for audio frequency magnetotellurics, or AMT. My name is Moira Poje, and I'm a geophysicist here at HGI. I have over 7 years of experience in data collection and processing for audio frequency magnetotelluric data and magnetotelluric data. I'm a member of AGU, AHS, the Earth Science Women's Network, and the Environmental and Engineering Geophysical Society, where I currently serve as a board member. I'm looking forward to spending the next couple minutes taking you through the what, why, and how of AMT and the ways in which it may apply to you and your site. Let's get started. How can an HGI geophysical study with AMT benefit you? AMT data can further inform your basin structure for a groundwater model, identify deep geothermal deposits, highlight conductive mine deposits, or differentiate between briny deposits and potential freshwater. I'm going to take you through why you would choose to use AMT at your site, the background of what the AMT method is, and how AMT is set up in the field. We'll also talk about potential opportunities for AMT to help in site characterization. AMT can see to greater depths than other geophysical methods and can provide a broad understanding of your site across a large area of investigation. AMT can help you identify areas of interest or drilling targets at a cost savings compared to other techniques. So what about you? Why is AMT the choice for your site characterization? I like to say, we do the science before you drill holes in the ground. AMT can be a great partner to a broader site investigation, whether that means basin characterization or an informed approach to groundwater modeling. At HGI, we have the capability to pair AMT surveys with other geophysical methods and a priori site information. As you can see from this image, AMT systems are highly portable and can be moved across project areas by hand or by ATV. This makes the AMT method highly flexible with survey design and during field work. AMT systems use natural electromagnetic fields for the source signal. Combined with the flexibility afforded by portable systems, this means that permitting for AMT geophysical surveys can be less taxing than other methods, which may require a high-powered source or vehicle access. Each AMT station setup collects data as an individual sounding. Soundings make it easy to evaluate for resistivity at depth from a single surface location because the depth of investigation during an AMT survey does not depend on the total length of the survey line like it may with other geophysical methods. AMT thrives where there is good electrical contrast in the subsurface material. For example, where conductive brines meet resistive alluvium. You'll see processed results of this example later on in the presentation. One example of this work is the partnership of electromagnetic surface properties as identified by AMT modeling, with bedrock highs and lows as identified by gravity modeling. On the top right is a three-dimensional plan view of gravity data collected over a field site, where blue areas are increased alluvial thickness and red areas indicate decreased alluvial thickness, and thus bedrock that's closer to the surface. On the left and bottom, two AMT depth sections show modeled resistivity values at depth. Surface distance is shown on the x-axis and depth on the y-axis. This combination of geophysical surveys can image to depths far greater than the capabilities of other geophysical surveys. Impressively, The depth of investigation for AMT data is up to 1 to 2 kilometers, or 3,000 feet below the surface of the Earth. The deep exploration potential lends well to geothermal exploration, characterization of brine extent, deep structural investigations, and groundwater and mineral exploration. An example of an AMT profile shows a decreased depth of investigation where the subsurface is very conductive in a brine zone, but increased depth of investigation where there are resistive sediments. The briny playa is indicated by the purple hues on the left, and the alluvial sediment is seen at the surface of the line in orange hues on the right. AMT is a geophysical method for inferring the Earth's subsurface electrical conductivity from measurements of natural geomagnetic and geoelectric field variations at the Earth's surface. As we explore the possibilities of AMT together, I'll explain the significance of lightning strikes to the source signal for AMT data collection. The phrase audio frequency magnetotellurics is an amalgamation of the frequency at which the instruments operate in the audio range and the recognition that the source currents are not man-made, but rather occur due to the natural electric field and magnetic field variations across the Earth. So as you can see in this image, we have the EM spectrum on the left and an image of the magnetic field lines around the Earth on the right. If you're familiar with the electromagnetic spectrum, it's important to note that we're looking at a particular range within this spectrum. Normally, we use radio waves to listen to our favorite talk shows, visible light waves to see the objects around us, and microwaves to heat our food. In this case, we're sampling frequencies that fall in the audio range, so between 10,000 Hz and 1 Hz, which are very long wavelengths compared to the examples that I just mentioned. These frequencies allow us to see what's below the surface of the Earth, up to 1 to 2 kilometers in depth. See the yellow circle in the image above. At certain frequencies, and thus certain wavelengths, the magnetotelluric signal is stronger. Some of these sources are micropulsations at the lower frequencies and the dawn chorus at higher frequencies. Lightning is also a contributor to AMT signals and occurs at frequencies between 1 Hz and 300 megahertz. You might be asking, how does the signal translate into something we can read on the ground? Well, EM energy travels as a wave in the atmosphere, but diffuses in the Earth. This type of signal propagation occurs above 1 Hz. The ionosphere and atmosphere of the Earth act as a waveguide for the electromagnetic signals. One type of electromagnetic signal in AMT is a lightning strike, as shown here. One way to think about the waveguide is to imagine that the wave is a bowling ball and the waveguide is the bumpers. A signal generated in one part of the world will travel trapped within the waveguide to other parts of the world. The resistive atmosphere acts as a waveguide between the conductive Earth and the ionosphere. At the AMT survey site, the signal propagates as a plane wave incident to the surface. That means that the signal diffuses down into the Earth below the surface and the signal strength decreases as it moves deeper into the Earth. Both the electric field component and the magnetic field component of the signal are perpendicular to the direction of signal propagation, as seen in this image. We can track the intensity of the electromagnetic interactions with our ionosphere with the planetary K indices, which are published by the National Oceanic and Atmospheric Administration. The AMT survey method is useful across a diversity of industries. This image shows the frequency ranges for RMT, radio frequency AMT, CS AMT, controlled source AMT, and magnetotellurics. Beneath these method classifications, you can see various industries and the depth of investigation needed for geophysical studies to be effective. For example, hydrology applications need to detect fluid flow in the shallow subsurface of the Earth, but structural geology requires a greater depth of investigation and thus a lower measurement frequency. Lower frequency recordings result in decreased signal attenuation and deeper penetration into the earth. AMT equipment is portable, data acquisition can be accomplished with a small field crew, and it doesn't require high-powered systems to generate the source signals. So how would HGI perform an AMT survey at your site? Let's explore how AMT data acquisition would work in practice. I'll take you through the basic steps of a hydrogeophysics AMT field survey, starting with field setup, moving to data acquisition, then analysis and processing, and finally our results and data interpretation. The crucial components in an AMT field setup are electric field sensors, which are typically porous pot electrodes, magnetic field sensors, which are typically magnetic induction coils, and a data acquisition system. Occasionally, it may be useful to implement an external transmitter at some distance away to account for frequencies that naturally have low signal amplitude. Our geophysicists at HGI can help determine if adding a transmitter is appropriate for your AMT survey. In this image, you can see two slides of a data collection box and a porous pot electrode in the center. Some examples of site setup involve running a field computer for real-time data analysis, orienting and leveling the magnetic induction coils, and establishing field stations in remote locations. You can see me on the left here, orienting and leveling a magnetic coil. The AMT Field Kit represents all of the different elements of establishing a field station for AMT data collection. As you can see here, the magnetic sensors are oriented perpendicular to each other at the field site. If your site requires a transmitter to supplement the low signal bands, the setup will be similar to this image. The transmitter tent is similar to the size of a camping tent. It's powered off of a 12-volt car battery, which is shown in the left image, and provides a good sense of scale for the transmitter setup. When establishing the transmitter, HGI considers near-field effects, transition zone effects, and signal proximity. A typical system has multiple data acquisition bands to maximize the range of data frequencies that are collected. There is a trade-off in imaging depth versus resolution when collecting AMT data. The lower frequencies, and thus longer wavelengths, help the user to image deeper into the earth. The long wavelengths do not attenuate near the surface, yet provide decreased imaging resolution. The higher frequencies, and thus shorter wavelengths, help the user to see shallower with greater resolution. The short wavelengths attenuate at shallower depths, and thus the increased resolution is a trade-off with depth of investigation. In this example, HGI collected data in a high, mid, and low band. Depending on the AMT system, there may be different data acquisition bands. Hydrogeophysics is diligent about quality control checks on AMT equipment in the field. The following are prioritized: alternating current as a measurement of cultural noise influence, and best seen on the magnetic coils; direct current, which is a measure of the potential difference in electrodes and their integrity; and contact resistance with the ground. Wires are regularly checked for any animal bites or potential wind noise interference in wire layout. Our field experts check the leveling and orientation of the coils as well. All attempts are made to locate AMT stations as far away from electrical or municipal infrastructure as possible. The combination of perpendicular electric and magnetic sensors provide good sensitivity for signal changes in time and space. The magnetic coils are more sensitive to changes in time and electric sensors are more sensitive to signal changes in space, as in, the electric field can vary significantly between different data collection locations. True tensor AMT would include a third magnetic sensor, a Z component, for the tipper and tipper magnitude. This is typically not feasible for a field production setup due to the logistical challenges surrounding wind noise affecting a vertical sensor. Cultural noise and infrastructure can affect any band of data, so it's important to reduce any human-made electrical noise while in the field. This can fall in the realm of laptop chargers, running trucks, and proximity to electrical infrastructure. The extent to which a band may be affected by noise sometimes is not realized until after the data are processed. Timing data collection with periods of low cultural noise is not efficient, so AMT survey design must take noise sources into account. Some field modifications that can be made are increasing stacking times or increasing dipole length. Longer stacking times may yield cleaner data depending on noise levels, and longer dipole lengths increase signal but may also increase noise, especially in the high band. Based on those concerns, take a look at this photo and see how many noise sources you can identify. Take a look at these arrows. You can see some vehicles in the background, several sets of power lines, and a railroad line. All of these features can be detrimental to AMT data acquisition. So hydrogeophysics will work with you to determine the best survey orientation to avoid close contact with these pitfalls. So we'll explore in a second here how these issues actually manifest in the data. To show you how this might manifest in the data, you can see here an example of AMT data from a station close to a power line on the left, and a station that is far from a power line on the right. There are many features in these plots, which are graphs of the apparent resistivity and impedance values on the y-axis and the frequency on the x-axis. Noisy data that are excluded from the inversion are noted in red. Draw your eye to the circled points on each plot. You can see that the left plot shows a group of power line contaminated points, which is in stark contrast with data at the same frequency from the non-contaminated station on the right. On each graph, there is a section of noisy points on the left at lower frequencies. However, even when there are not significant problems with electrical coupling contamination, errors from power line data can influence data quality on smaller levels. In the United States, the frequency of a power line is at 60 Hz. This is a station in close proximity to the power line. While the overall character of this apparent resistivity AMT curve is fairly clean, there is evident contamination at the 60 Hz frequency and several harmonics of that frequency. Again, there are noisy points at lower frequencies due to the lower limits of AMT data acquisition bands. AMT data collected over an alluvial fan shows variation in resistive layers. Note that a scale in log resistivity is on the bottom of this plot. There appears to be a three-layer system in this example. A layer of orange-hued, resistive layer, bounded by a thin superficial, more conductive layer on top, and a thick, more conductive layer at depth. Maximum depth of investigation in this example is nearly 3,000 feet. Note the depth of investigation of the AMT data may depend on the conductivity and resistivity of the subsurface. The depth of investigation in the conductive zone is only 1,000 feet, and the depth of investigation in the resistive zone is almost 3,000 feet. While AMT allows for the user to see significant depths based on its per-sounding methodology, it still behooves the user to decrease the station spacing to better understand the dynamics of their subsurface system. For example, you can see that the characteristics between stations B21, B22, and B23 on this plot are lost due to the large station spacing. The large station spacing means that the resistivity values displayed in between those data collection locations may be significantly dependent on algorithmic smoothing factors and not the actual characteristics of the subsurface in question. In summary, while cultural noise and electrical interference can affect data quality for AMT, the flexibility of survey design, scalable exploration size, and options for large depths of investigation make this a great tool for characterizing the subsurface. AMT can image up to 3,000 feet below the surface of the Earth. It can serve as a partner for depth to bedrock surveys with a gravimeter, or see beyond the limitations of high-velocity layers in seismic surveying. AMT surveys can provide broad resistivity characterizations spatially and at depth that can enhance your understanding of what's happening beneath the surface of your site. AMT surveys by HGI can improve your target identification and your efficiency of site characterization. Compared with other geophysical methods, it can save you time and money as you work to better understand the subsurface properties at your site. Any further questions? Give us a call at 866-647-3315 or drop us a message. We're always happy to talk about how geophysical methods can benefit you and your site characterization.